Here we're going to do question 2 from the 2015-16 exam paper. So this is 2015-2016 question 2, and this is on Turing instability. So let's start with part 1. So we're given a couple of chemicals reacting and diffusing together, and they satisfy these equations. Du by dt is F plus Uxx plus Uyy, and Vt equals G plus D Vxx plus Vyy, and we're given the particular forms of F and G. So F is 2 into 1 minus U plus U squared V, and G is U minus U squared V, which perhaps it will be helpful to note that we can take U out as a factor there to write it like that. Okay, so question A, we're asked what does the symbol D represent? So D represents it's the diffusivity D, and since it only appears in the V equation, the diffusivity in the U equation is implicitly 1. So D represents the diffusivity of chemical represented by the symbol little v. Right. What are the reaction equations? What are the reaction terms, rather? Perhaps it's simplest to circle those. Let's say the reaction terms are circled. Well, these are the terms F and G. C. Give two algebraic relations satisfied by U0, V0, the spatially uniform steady state. Okay, so for a spatially uniform steady state, U0 and V0 are both constant. Okay, spatially uniform means it doesn't depend on space. Steady state implies it doesn't depend on time either, so they must be constant. Okay, so they must therefore satisfy, from the U equation, if U is a constant, F must be 0, so we must have F of U0, V0 is 0. And from the V equation, if V is a constant, then G must be 0, so G of U0, V0 must be 0. We're given the particular forms, so that means that using the form for F, 2 into 1 minus U0 plus U0 squared, V0 has got to be 0. And using the G form, then we've got U0 into 1 minus U0, V0 has got to be 0. Right, so from the second equation here, you can see that either U0 is 0 or this bracket is 0. So let's consider the first possibility first. U0 equals 0, which knocks out the second equation, satisfies that. But then the first equation gives me, well, I'm taking U0 to be 0. So F of 0, V0 is then, take U0 to be 0, you get 2, which is definitely not 0, so that's not possible. So you must exclude this possibility. In other words, U0 can't be 0. Well, the other option here is that U0 is 1 over V0. So let's try that. So if I take F of U0 and then 1 over U0, because V0 is 1 over U0 now, then what have I got? Plugging that into F, that's 2 into 1 minus U0 plus U0 squared divided by U0, replacing V0 with 1 over U0. So that's 2 minus 2 U0 plus U0. Looks like being 2 minus U0. So if that's equal to 0, I must have that U0 is 2. So that would work. So there's a unique spatially uniform steady state, and it is U0, V0 is equal to, so U0 is 2 and V0 is 1 over 2, so it's 2, a half. Right, okay, now we can move on to part D. Write down the inequalities involving F, G and their partial derivatives, which must be satisfied for U0, V0 to be stable in the absence of diffusion. So these are the inequalities that we just had to remember. So it's the trace of the Jacobian df by du plus dg by dv has got to be less than 0, and the determinant of the Jacobian fugv minus fugu has got to be positive where fu means df by du at u0, v0, etc. with our usual bit of notation. So let's work out these partial derivatives. Now, df by du is equal to, so let's go back up to the form for f and differentiate it with respect to u. So we're going to get minus 2 from that term plus 2u0 v0 because we're evaluating at the base state. Df by dv is just u0 squared. dg by du, so here's the form for g, it's probably the easiest one up here. So that's 1 minus 2uv, u0 v0, and dg by dv is minus u0 squared.